Okay, this is week 11 of ELTE131, Motion and Machine Controls. What are we going to be studying this week? Well, we're going to be talking about solenoids, valves, and cylinders. At the end of this week, you're going to know how to explain and operate solenoids and valves and create a circuit off of ladder logic for a pneumatic cylinder. There's a lecture worksheet that follows this video, and if you're watching this video, you've downloaded the PowerPoint and you've clicked on this video link here. You're going to need to stop once in a while and fill out your lecture worksheet. Let's start with a proximity sensor review. So proximity sensors allow non-contact sensing using a field. You don't actually have to touch something, you just get within the field. Capacity proximity sensors use an electrostatic field, and they're affected by dielectric greater than 1.2. So we saw that styrofoam didn't do it, but if you had a bottle full of liquid, the liquid would set it off. And it sense just about anything. Inductive proximity sensors use an inductive field to sense ferrous metals. And then Hall effect sensors use magnetic fields. So that was our proximity sensors. We talked about photosensors, and they used light to allow non-contact sensing. They were separate, were emitter and collector opposite sides. Talked about a light curtain. Retroreflective uses a mirror, and we demonstrated polarized versus non-polarized. So the polarized gives you even a little more specific operation if you need that. And diffuse, the natural reflective properties of the material. So there's also a variety of other sensors we talked about, for example, ultrasonic that might deal with sound. And we took a look at some homework and some labs. So I encourage you to pause the video and check the homework here. You can click this link and see how your homework compared to this. I kind of talk you through some of it. It's going to be just like this on the quiz. And the sensor lab answers can be found here. So here it takes a little while. I go through the sensor lab, and you can compare your answers to what was here so that you're able to pass the quiz. So this week we're talking about motion. So we're going to start talking about electromagnetic motion. So we've learned that magnetism can be used to create mechanical motion. We've learned that rotary motion, when you use magnetism and electricity, is called an electric motor. We're not going to get into electric motor right now. We're talking about creating linear motion using electricity and magnetism. We accomplish this using a solenoid. So electric motor for rotary and a solenoid for linear. Okay. What is a solenoid? They use magnetism to create linear motion. So here's a cutaway of one. Hopefully it makes sense to you. This is a coil of wire here, this winding here. It's a cross section. So when you run current through there, you get a magnetic field. And so when that magnetic field comes online, you have an iron or a steel plunger here, and it gets pulled in towards the magnetic field. And then when you remove the current, the magnetic field goes away, and then a spring pushes it back out. So this is linear motion, in and out, depending on whether there's a magnetic field or not. Okay. Solenoid operated devices. There's quite a few around. Let's go back to your 109 days where you had the buzzer boards, those bells. So your doorbells there were solenoids that were just pulling a ringer in and out and hitting it up against a steel annunciator. There's mechanical latches that you could use a solenoid to pull that in, maybe like in your car doors. Valves use solenoids. That's what we're going to be studying today. Relays use this solenoid actuated device. You run it through a coil, and it pulls the relay in, and the plunger comes in, and the contacts are make or break. So there's some solenoid devices that you might be familiar with. Just want to remind you of the solenoid characteristics because it's a coil. When you first energize it, you're going to get a very high inrush current here. And then as the solenoid starts to move, and it moves to the position where it's supposed to be, this inrush current settles down a little bit, and then you have your steady state current. You must protect the circuit at a level that's above the steady state current. So let's say the steady state current is 12 amps. Maybe a 15 amp circuit breaker would work, okay? But you wonder, well, this exceeded that 15 amps in this shaded area. Yes, you can do that for a very short time, and that is your time delay. So your delay has to be long enough so that you get underneath the circuit protection and then steady state so the circuit protection doesn't trip. So what affects this operation of a solenoid? Well, the pull. What is the solenoid pulling against? Okay, so let's say you have a solenoid that's pulling the locks on your door. Whatever that takes, is it a pound, 2 pounds, a half a pound? That amount of pull that it's pulling could cause this to spike up higher or lower, right? The stroke length. How long of a pull is that solenoid? The longer it is, the more this current's is gonna spike up, and the longer it's gonna take to settle down in here. A very short pull, it just might pop up and then settle in real quick. Impact forces, it's kind of a violent situation when you activate a solenoid. It kind of slams, and so does the solenoid bounce back and forth a little bit, or does it just activate? So impact forces associated with it. Those are some of the things that affect how much initial current it draws here, this area here, when you energize it. Okay, let's move on to fluid power and motion. What is fluid power? It's the use of fluids under pressure to control and transmit power. Okay, hydraulics uses a liquid such as mineral or oil, and pneumatics uses gas or air. So let's take a look at hydraulic fluid power. Maybe you see this on like big machinery like bulldozers and big backhoes and stuff like that, where they have these huge hydraulic cylinders. Well, that hydraulics operates at a pressure of, a couple of thousand pounds per square inch, or PSI. The benefits of that is that you really get a lot of force out of those cylinders, okay? A lot more. They're very high pressure, a lot of force. That's the benefit of that. But the drawback is you could end up with a very loud system. That system leaks a lot, and that system can catch on fire because hydraulic fluid burns, okay? Whereas pneumatic, that uses air, and we'll be using compressed air to move a cylinder, and you see a lot of this in automation. The benefits are that it's clean. If air leaks, big deal, right? Compared to hydraulic fluid, it's not combustible. And it's readily available. Most shops have an air compressor system that you can access the air. The drawbacks is it's not nearly as powerful as hydraulics. Okay, so you need a lot of force. Then you end up with pneumatic components that are quite a bit larger than the hydraulic components. Okay, so fluid power applications. We can use motors to produce rotary motion, similar to we use electricity to create rotor motion with electric motor. We can have a fluid motor, okay? And fluid cylinders can produce linear motion. So that's similar to using, with electricity, the solenoid, okay? So we can get rotary and linear motion using fluid power as well. What's that look like? Here's a fluid motor. This is a vane type compressor. The air comes in, it pushes on the vane, so in these pockets there's pressure, and it gets sent around and then exhausted on this side, okay? And so this will spin, creating rotary motion, called an air motor or a fluid motor or hydraulic motor. What we're really studying in this week is the cylinders, okay? So the way a cylinder works is you're going to have a piston inside of here, okay? And when you put pressure on this side, you get higher pressure on one side of this piston, and therefore the piston is going to move out, okay? And when you want to retract it, you run pressure into the other side right here, and the piston moves this way, okay? So that is a quick summary of what we're doing, and hopefully there was a lot you understood it from the reading that we're using cylinders here with pressure on either side. There's a lot of mathematical relationships that govern the behavior of fluid power systems. There'll be a little bit of this on the quiz. So go ahead and stop right now and watch this short video on fluid power. Okay, we're back talking about Pascal's law. So pressure acts perpendicular to the confining chamber of the fluid. So if there's pressure in here, this pressure is pushing outwards on this, and it's pushing, let's say this was a tank, it's pushing outwards this way, and it's pushing down and up. It pushes all around, okay? Perpendicular to this confining fluid, all right? And so if this was my piston, it would be pushing out, and then the force to hold it down would have to counter that, or else this piston would move, okay? So this is the pressurized fluid here, and if you pressurize something too much, it just explodes, I think, okay? And it explodes outward, perpendicular in every direction here. So that was Pascal's law that you learned about. So pressure is force divided by area. So what we're showing right here is a cylinder that has a radius of 2 inches. So that's the radius from the center of this circle out. Okay, so that means a diameter of 4 inches. 1,000 pounds of force is applied to this plunger. How much pressure do we get in here? Okay, and the video showed that pressure is force over area. So my force, I said, is 1,000 pounds. That's what I'm pushing down right here with 1,000 pounds. And area is pi r squared. So pi times radius, that's what that is, where pi is 3.149. So area is pi r squared. So 1,000 divided by pi radius squared would be 785 pounds per square inch. Okay, so this would be pounds per, oops, let's just do that. Does that let me do it? Well, that would be pounds. Oh, not gonna let me do it. Per inch times inch. There we go. Pounds per square inch. Sorry about that. So 785 psi. Okay. Boyle's law. This is as volume decrease, pressure increases, and vice versa. Well, that makes sense. If I have a jar right here and I smash it down, well, then the pressure goes up in here. And as I open it up, the pressure decreases. So this one over here would have a higher pressure than this one because the volume got less, okay? As volume decreases, pressure increases. That's the relationship there. So what does that mean when we take Pascal's law and Boyle's law and talk about it? It talks about transmission of power. So in this case, here is how this works. And it might be similar to the braking system on your car, okay? The force is exerted on a small cylinder, a small area over here, pi r squared. Let's say this was a round cylinder. Well, when you do that, you generate psi pressure in this fluid right here. And it's continuously throughout this, okay? And so it says surface 1 has an area of 2 square inches. Pi r squared was 2. And it generates a force of 100 pounds, okay? And then here's your brakes over here. So the brakes are going to have a larger cylinder on this side. And so the PSI that you have generated in here with your foot on the small cylinder, that PSI gets applied to a large cylinder, okay? So if this cylinder 2 over here has an area of 10 square inches, what's the force? Well, it's the ratio of the two, the small cylinder compared to the big cylinder. So if this was 2 square inches and this was 10 square inches, it's 5 times the force. So if you push down here with your foot of 100 pounds, then on this side you get 500 pounds of force in order to stop your car. So that is the transmission of power. That is how fluid works right there. And it makes sense. If you want to run a big bulldozer or something like that, well, you have a small cylinder over here that pushes down, and it generates 2,000 pounds or 2,000 psi in this fluid. And then over here, you put a big cylinder on your bucket or your plow, your blade, and then that generates a lot of force to move things around. Okay, so that's how the ratio, and that's how that works. In a shop, in a facility, you're going to have compressed air, and it usually cycles between maybe 80 and 120 psi or 90 and 120 psi, depending on how you set your pressure switch. And you're going to have a central compressor. And so what this does is it takes air, ambient air, and it compresses it. Well, when you compress air, it gets hot. Okay, so if you were to touch the top of these cylinders up here that are compressing them, they'd be hot. Not because there's any electricity or anything going through them. They get hot because they're compressing air. And so this air gets compressed and it gets put into a big tank here, okay? And it's under pressure. So it wants to explode, but the tank is containing it. And then the air cools, and then it loses a little bit of its energy, a little bit of pressure. But after a while, this will stop at whatever pressure, 120 psi, and then we'll have a tank of air. And then basically this compressed air is then piped all over the facility and delivered to your field devices, and that's what we'll be talking about today. So that's the way this works. In your PowerPoint handout, there's a big explanation of the components of shop air, and you'll want to understand how they work. So here's the really important stuff for our lab. There's two main classifications of cylinders. There's single acting cylinders that have a spring that extends or retracts that, and then compressed air works opposite of that. So let's take a look at this. This is my piston here. If I push air into this space, pressurized air, this rod will move out and you'll get linear motion. When I remove the air, this indicates that there's a spring here. The spring will retract it. So in this case, pressure extends the cylinder because it goes in this cavity here and pushes on the piston, and the rod goes out, and a spring returns it. Okay, and I'm going to show you some examples later of spring return cylinders versus double acting cylinders. Double acting cylinders have ports on both ends. So if I put some pressure on this end and push it on the piston, this rod will extend. Okay, and then when it extends, it might extend out to maybe like right here, right? The piston will be here. Well, then I can put pressure on this side, and that would cause it to retract. Okay, so pressure to extend, pressure to react. And then you'll see that what's different about these is, if I go back to here, this pressure on this side is what causes that to extend. So if I want more force coming out, put more pressure here. This spring right here, I can't adjust that. So the retraction force is whatever that spring is. If it binds up or something like that because the spring's not strong enough, there's not much you can do about it except replace that. Whereas this pressure pushes it out and pressure returns it. If you want more force, either extending or more force retracting, you can just up the pressure on either side of these and it will generate more force. Okay. Directional valves. So the number of directional valves control the flow. Okay, and there's a lot of ways and ports, and there's ways that the air is exhausted. We're going to break this all the way down, these directional valves. But before we get into it, I've got a little video here about the trainer that we're going to be using. Okay, I want you to take a look at this, stop it, and then as we go through this, it will make a little bit more sense to you what we're talking about. Okay, valve actuation. So a valve spool is an internal device to the valve that directs the airflow. Okay, so this is in your handouts for this week. You really want to study these and understand how they work. So it looks like there's a lever here that causes this valve spool to go back and forth. Okay, and so on the high side here, it's sealed. So if I look over here, the high side is sealed differently on this one. Okay, so that when I pull this back, it looks like the air it comes into here, and because this is now open, it goes to the front and it pushes on the piston and it comes down to the blind end and then it comes, and now there's a leak path here, and it exhausts. So with this lever out, it looks like air is going to cause this to retract. Now, if I push this forward, I change the way the air leaks. It changes a different path. So instead of going to the front of the cylinder, you can see the pressure comes in. It now goes to the back of the cylinder, and then the piston goes out, and then it leaks. Okay. So a couple of things about this. These are in your lab packet. You will really want to take a look at them. Okay. It is critical in this case to put this exhaust air out to the atmosphere, because if we did not leak the air out on this side, on the rod end side, when we were pressurizing the blind end side, we wouldn't get a very good result, because we might have 100 psi here and we might have 100 psi on this side. Well, they're almost equal, pushing on each other, and it wouldn't go anywhere. But if we let this air leak out here completely, well, then it moves. Okay. As a side note, if we did put 100 psi here and we accidentally put 100 psi here, this rod would still extend, because the area is pi r squared on this side. On this side, it's pi r squared subtracting the rod right here, which is pi r squared. So this side actually has just a little bit less area because there's a rod here that's taking it up. Okay, so the lever here activates the valve spool back and forth, but what we're going to be doing is we're going to be using an electrical solenoid that moves this valve spool back and forth to automatically direct the air. That's the lab today, using electricity to move the valve spool to create linear movement in an air cylinder. Okay, so as we go through our valve positions, this will be on the quiz, so you definitely want to understand. Boxes indicate the number of positions. This sounds pretty simple. One box, two positions. One box, one position. Two box, two positions. Three box, three positions. That's my valve positions. My valve ports, or my ways, are just the number of connections around it. So if you look here, I got one. I don't have any on this side. I've got one on this side. I've got two. So I've got two touching the box. It's a two-way valve. This one, we want to start here. There's one. There's an on this side. There's two. There's three. And there's none. So there's three there. Got it? 1, 2, 3, 4. That's a four-way valve. And this is 1, 2, 3, 4, 5. Okay? And these are the symbols that you just saw in the video for the trainer. I said they're very hard to read sometimes on a valve because they're super small, but they tell what's going on. The flow direction. Arrows indicate the flow of the direction. Okay, so this right here is a T. Okay, a T indicates that the port is teed off, that there is no flow. Okay, and lines or connections are only drawn to one valve position, indicating the normal position. So let's take a look at this. This is showing two positions. Okay, the first position, it's teed off. All right, then in the second position, when it's actuated, it allows the air to flow. So it's either blocked, it's either off, or it's on. Two positions. The first position off, the second position on. Looks like this is the same right here. This is another two positions. The first position, it looks like air comes and it goes to the right port, and in the second position, air goes from the left port out. So we'll be taking a look at some more of these right here to understand how to read these. Okay, couple notes. So electric solenoids change the valve position by directly moving the valve element, and they're just called direct solenoids. So if you went back to here and we put a solenoid on here, it'd be a direct solenoid moving that back and forth. Okay, versus electric solenoids that open small pilot valves and allow pressurized air to move, these are piloted valves, okay? The air does the work. Doesn't require very much electricity at all. So piloted valves use less current than direct solenoids. It's kind of a combination of the air pressure and the electricity. Piloted valves are what you're going to see out in the field, okay? Valve symbols. Here's my air piloted. Here's my solenoid, direct solenoid. And here's my solenoid air piloted. These are kind of what we'll be using right here because we do have electricity causing the valve spool to move, but it's helped along a little bit with a piloted valve, okay? So let's take a look at some valves and let's classify them. Let's take a look at this first one. I say it's two position because it's got two boxes on it. So two position, 1, 2. It says two ways. Okay, but look, you say, wait, 1, 2, 3, 4. That's 4 ways, isn't it? No, it's not. You only look at one of the positions here, and you'll see that there's 1, 2. Okay, if you look at the second position, 1, 2. So there's 2 ports on this. Okay, and so it's got a plunger here. It looks like there's something on the end here that if you push it, it causes it to go back and forth, and a spring returns it back to the other position. So it's either closed or open. Okay, if I push this item right here, it changes position, and when I let go, the spring goes back. Let's take another one here. 2 position, 1 square, 2 squares. How many ways? 1, 2. And this is a direct solenoid, and it has a spring return. So the solenoid causes it to move. When you break electricity to the solenoid, the spring returns it. Let's do some more. 2 positions, because I got 1, 2 boxes. 4-way, how come? 1, 2, 3, 4 connections to each box. This box also has 4. 1, 2, 3, 4. And it's air piloted valve with a spring return. That's what this is showing here. One more, 2 position, 1 square, 2 square. 4-way, oh, this should be a 5-way, it looks like. I'm going to change this to a 5-way. 1, 2, 3, 4, 5. This is a 5-port valve, not a 4-port. 1, 2, 3, 4, 5. So this should be 2 position, 5-way. And this is air piloted with spring return, okay? So that's where we're at on that one. A couple of other pneumatic components. You need a compressor. Air receivers are junctions. Kind of looks like when you build these up, it's similar to building up a control diagram. You would look for service equipment, filters, lubricators, separators, and this is the symbol for a regulator. And I want to remind you, and I'll say this a couple times, when in doubt, meter out. And I showed you that in that prior video. You're going to want to remember that. A couple more. Here is a adjustable flow control right here. That means it limits how fast the air goes out. Checked valve. This means that air can only flow one way, because when it tries to flow the other way, this ball gets seated in here and it can't flow. So it only allows air one way. Piloted operated check valve. The air affects the way that this is checked here. An adjustable flow control with a bypass. Okay, and I want to you'll see these quite a bit. I want to remind, when in doubt, meter out. Okay, so here's a big one. Here are operation of 325253 in fluid sim components. You're going to want to stop this, and each one of these is about 2 minutes, and watch how the valves actuate and the change in flow through the valve spool works to cause the cylinder to extend or retract. So definitely want to stop and watch these videos so you understand what's going on. So I'm going back to this as my PowerPoint handout. You're going to have a lot of these hydraulic or pneumatic 2-position valves. It shows you that this has 1, 2 positions, and there's there's your pressure port, and there's your exhaust. So 4, 1, 2, 3, 4 ports. It talks about what the actuator is, whether it's a spring actuator or solenoid or manual lever. There's a bunch of these in your handouts, and then you can check and see the way that the valve spool causes the air to leak around it to either extend or retract or to tee off these valves. Okay, study those, because those are the things that are important to the quiz in the lab. The lab, here's the first circuit on the lab. This is, if you look down here, they've got the circuit drawn. 1, 2 coils, okay? 1, 2 coils. I see 1, 2, 3 squares here. So this is a 3-position valve. So in the middle position, it looks like everything's teed off, nothing's happening. In this position here, it looks like air is passing straight through. And then in this position here, it looks like the air is crossed, okay? And this is shown in the video that you just watched, how this works, how the valve spool works, okay? And then here's your control circuit that you'll be wiring. Notice that this right here is a fuse. 5 and 6 are the fuses for the control circuit here that allows memory to occur and to turn on the control relays, and the control relays do all your logic of unlatching and latching, and depending on where your limit switches are. These fuses on the end here, 4 fuse and 7F, this goes to 1, so this goes to here. These are my solenoids, 1 solenoid, 2 solenoid. So I've got 1 solenoid and 2 solenoids. That's the way that works. If one of these fuses gets blown out, well, your valve is not going to work anymore. But your control circuit will still be online, so you can try and troubleshoot what is going on. That's the purpose of these additional fuses here, okay? Also, each solenoid has its own fuse. So you might blow up just the fuse, or burn up just the fuse for the first solenoid right here, okay? At which point this solenoid will work to try and retract it, but it won't extend. So these fuses are multiple levels of fuses to control how this is working. Because these are now air piloted valves, they don't use very much current, okay? And a lot of them are DC these days. So you might not necessarily see all this extra fusing on here. But if you have AC coils that are direct solenoids, you certainly could get into a position where you could blow these fuses. And if these were very big valves, maybe hydraulic valves, you might see something like that, okay? So this is the circuit that you would build, and it looks like this PB causes the control relay to have memory, and then depending on the limit switches that are hit that we showed you, it's going to then break this memory, and when it extends, turn on 2 CR. So it looks like 1 CR turns on the first solenoid to extend it, and because if you follow the air right there, it goes to A and B. And then the second, the limit switch kills the first CR, causes the second CR to come on, which turns on the second solenoid, causing it to retract, okay? Study this circuit. Be sure you understand what's going on. Circuit 2 is a little simpler because this has a spring return. So we only have 1 solenoid, and you'll see 1 control relay. When that control relay comes on, here and here, that solenoid is activated. And when it comes out and it kills the limit switch, when the limit switch hits it, it just turns that off, turns this off, turns that off, turns that off. What happens? The spring pushes the spool back, and the air, instead of being redirected to extend it, the air is redirected to retract it. So study this circuit very carefully, okay? At this point, you're finished with lecture turning lecture worksheet. I encourage you to stop and watch a couple of those videos again to be sure you understand what was happening.